Okay, so welcome to the seminar of the Sony Astani Department of Civil and Environmental Engineering. So today we are fortunate to have Dr. Loh, Kenneth Loh, who is an assistant professor in the Department of Civil and Environmental Engineering at the University of California, Davis. He received his BS degree in civil engineering from Johns Hopkins, and I believe Roger was his undergraduate research advisor at Johns Hopkins. So he received his BS in 2004. Then he continued his graduate studies at the University of Michigan, where he completed his MS degree in civil engineering in 2005 and completed also a second MS degree in material science and engineering in 2008. He also obtained his PhD degree in civil engineering in 2008. His research interests include the development of multifunctional nanocomposites, biologically inspired materials, that sounds good, for sensing actuation and power harvesting application and wireless sensing. So let us welcome Dr. Loh. Thank you very much.
Great, thank you again for the kind introduction. Again, my name is Kenneth Loh, and the title of my presentation today is Nanocomposite Sensors for Distributed Structural Monitoring and Damage Detection. Now, before we jump into the technical aspects of this presentation, I think it's important for us to take a step back and just to reiterate some of the roles we have as structural engineers. So as many of you know, as structural engineers, we are largely concerned with the design and construction of large-scale and long-span structural systems, like the San Francisco Bay Bridge. Or oftentimes we are interested in designing mid-rise apartment buildings or even underground pipeline networks, among many other different types of civil infrastructure. However, as you all know, all these different types of structural systems are subjected and susceptible to structural damage. For instance, we know that our large inventory of structures are currently aging, and that there's a large effort to renew our current inventory of aging structures. For example, the construction of the new Bay Bridge in the Bay Area. Also, for structures situated in seismically active regions, we require performance-based design methodologies as well as hazard mitigation techniques in order to prevent structural failure. And other types of structural damage include structural deterioration due to environmental effects like corrosion. But regardless of the type of structural damage that we're interested in, we know that in order to prevent structural failure, there is an urgent need for long-term sensing technologies in order to monitor structural performance. However, even today, the current base management approach is still largely reliant on visual inspection. In terms of bridges, the National Bridge Inspection Program requires biannual inspection, visual inspection of our current inventory of bridges. Now, when it comes to visual inspection, typically we require a trained engineer to go on site of the particular bridge and to basically crawl around the bridge structure to visually try to identify for signs of visual damage, such as cracks, corrosion, among many other different types. But as you can imagine, when we have a trained engineer on site, it's incredibly difficult to access every location and to identify every little damage. And as you can imagine, the procedure is extremely expensive and labor intensive. But what's more important when it comes to visual inspection is that we are at the mercy of the trained engineer on site and his subjective opinion whether or not structural damage is serious enough that it warrants a rehabilitation or even a reconstruction. Now, so as to add more quantitative measurements in terms of different structural management approaches, many researchers as well as practitioners have relied on permanent monitoring systems to monitor the performance of these structures. Now, most of these permanent systems have been based on cable-based or tethered monitoring systems. And typically, this involves the instrumentation of simple sensors like accelerometers or even strain gauges onto various locations of a structural system. Now, in order to communicate with these sensors, as well as to provide power for these simple sensors, we typically require long lengths of coaxial cables connected to some base station or centralized data repository. But with these long lengths of cables, it comes associated with them very large or very high installation as well as maintenance costs. And each sensing channel can cost up to $3,000 per channel. And as a result of this high cost, we can only rely on very low sensor densities installed per given structure, simply because of the economic constraints placed on such a system. Now, to overcome these inherent challenges, there are currently many different emerging sensing technologies currently being developed in industry and in different laboratories. For instance, wireless sensors and sensor networks are currently being researched, and their main objective is to eliminate our reliance on these coaxial cables, and also to furthermore distribute our computational power to these individual wireless sensing nodes. Other different types of technologies include ultrasonic and guided waves, which will allow us to actively interrogate the structure and to basically query the structure at any desirable time that we wish. Another different class of research involves the utilization of integrated circuits technology as well as microfabrication techniques to develop more advanced sensors, such as microelectromechanical systems or MEMS-based devices. But regardless of the type of the different advantages and disadvantages these different sensing technologies have to offer, what I'd like to present to you today is a different approach. But before I do that, we first need to consider this main question. With all these different sensing technologies available to us today, why are there so few structural health monitoring systems utilized in practice? Well, first of all, most of the sensors that we have available to us rely on indirect sensing approaches. The sensors that we use do not measure damage directly, but rather they measure structural performance. And we require physics-based models or even statistical algorithms so as to estimate whether damage has occurred or not. Second, most of these sensors are point sensors or discrete sensors, in the sense that these sensors can only collect data or measure structural performance at their particular instrumented locations. And if we wanted to be able to identify damage between sensor locations, again, we require some type of algorithms or interpolation scheme in order to perform that task. Most of these sensors are also tether sensors, and as I mentioned before, cables are extremely expensive and are not scalable for large-scale systems. And furthermore, there's also a lack of systems scalability. Now, in terms of the structural health monitoring paradigm, the current approach is to instrument a dense sensor network in a given structure, which will allow us to collect as much information as possible. But with so much data being generated by each sensor, and as we scale up the number of sensors, this poses a significant computational demand on your centralized data repository. And this aspect also needs to be addressed. And finally, there's also the issue of an incompatibility between the data that's obtained as well as decision making. Now, Professor Ghanem and Professor Masri here at USC are pioneering the work to look at structural prognosis techniques to facilitate the transfer of measuring structural response and how that transfers to what the next step will be, whether a structure needs repair or it has still 5 years of remaining service life, things like that. But for today's example, I'd like to shift our attention to a next generation structural health monitoring paradigm. And the main objective of this study is to address some of the challenges associated with current structural health monitoring technologies. And that is, our objective is to achieve 2- or 3-dimensional spatial sensing, and we want to be able to detect damage directly. Now, to achieve this goal, we're going to design a new class of sensors, but in order to meet these 2 design objectives, you can imagine that the sensor needs to be conformable so that they can be coded onto large structural systems. And in order to perform direct damage detection, as well as 2- or even 3-dimensional spatial sensing, the material needs to be sensitive to damage at every location of the material. Now, for it to be robust, it also needs to be mechanically strong. And when it comes to monitoring structural performance or damage, we know that there are different effects that we want to consider. So ideally, we want to be able to encode multimodal sensing capabilities within this one material system. Now, to achieve these design objectives, we're going to rely on a bottom-up sensor design methodology. This is in direct contrast with current sensor fabrication technologies, which will rely on a top-down design approach, where if you look at microelectromechanical systems designs, the current idea is to take a large-scale design concept and try to miniaturize this design into a small and compact device using different integrated circuits processing or different etching tools that we have. But instead, with a bottom-up sensor design methodology, we want to be able to have control even at just molecular or atomistic length scales so that we can manipulate these materials and scale them up and escalate their material properties to intentionally tailor a nanocomposite with desirable mechanical and electrical properties for monitoring structures. Now, to better illustrate this process, we can begin at nanometer length scales, looking at individual molecules of polymer or even carbon nanotubes, and try to precisely control its microstructure and utilize self-assembly approaches in order to organize these microstructures in order to create our final multifunctional nanocomposite that we can use for structural health monitoring. So for today's presentation, I'd like to begin by talking to you a little bit about how we developed our carbon nanotube-based nanocomposite and how we can tune its electrical and mechanical properties for different sensing applications. Then I'll move into the discussion of how we can combine this nanocomposite technology with existing passive wireless sensing technologies in order to create a distributed passive wireless sensor. But finally, to transition from a point-based sensing approach to a truly distributed spatial sensing structural health monitoring paradigm, I'd like to introduce to you some of our recent work on our bio-inspired sensing skin. So first, the development of carbon nanotube-based nanocomposites for multimodal sensing. Now, the material of choice that we've employed are carbon nanotubes. And in case you don't know what a carbon nanotube is, its physical structure is simply a graphite sheet or a graphene sheet that's rolled to form this cylindrical structure. Its physical structure is characterized by a diameter of approximately 0.4 to 10 nanometers. But what's most impressive and unique about this material is its incredible high aspect ratio. That is its long length. And also associated with that high aspect ratio is an incredible large surface area. Now, this surface area is extremely advantageous for us because we can actually modify the intrinsic material properties of an individual carbon nanotube by molecularly attaching different species onto its surfaces, also known as functionalization. But when we look at just a pristine carbon nanotube in itself, it already exhibits impressive material properties. For example, its mechanical strength is 200 times stronger and 5 times stiffer than steel. And electrically, it can be metallic or even semiconducting, depending on how you roll your graphite sheet to determine your carbon nanotube structure. Now, in addition to these impressive material properties, many researchers have also wondered whether we can use these carbon nanotubes directly to build a sensor. And in fact, Hongji Dai's group at Stanford University have pioneered this work to look at the piezoresistive response of carbon nanotubes. And that is whether the electrical properties of carbon nanotubes will change under applied strain. So what they did in their study was they've been able to isolate an individual carbon nanotube and then suspend it over a patterned silicon trench. Then, using an atomic force microscope tip, they can apply 3-point bending to this carbon nanotube while simultaneously measure the vertical displacement that they apply, as well as the change in conductivity, G. And from these results, from Hongji Dai's group's paper, you can see that this material behaves as an excellent strain sensor, where the conductivity of the material will decrease in tandem with increasingly applied displacement. And by displacement, I mean the 3-point bending displacement. And in fact, even at just 3% axial strain, the conductivity of the material can decrease by more than 2 orders of magnitude, thereby suggesting that this material behaves as an excellent strain sensor. But as you can imagine, even though carbon nanotubes exhibit excellent inherent piezoresistivity, it's very difficult to scale up this material into real-world structural health monitoring applications, simply due to their small size. So if you imagine, it's very difficult to isolate an individual carbon nanotube and place it on the Bay Bridge to monitor your cracks. So alternatively, many people have looked into how we can bridge this nano and macro gap. And that is, how can we translate the impressive materials exhibited at the nanoscale domain into tangible length scales, into devices that we can actually use every day. Now, in order to do so, one of the most straightforward ways to accomplish this goal is to combine carbon nanotubes into some composite thin film system. And the current thin film fabrication techniques that have been able to achieve this goal is namely for bucky paper fabrication, and that is to separate individual carbon nanotubes in a solution and then vacuum filtering it and then drying the filter to create this thin film structure. Other techniques include epoxy molding, that is to mix carbon nanotubes with some epoxy resin and curing it, or even thermal evaporation and annealing. But unfortunately, these different thin film fabrication techniques are essentially brute force techniques. That is, people are just trying to forcefully embed carbon nanotubes within some type of matrix system. And it is because of this lack of nanoscale and microscale control that the final material properties of the composite system is essentially quite poor. In fact, if we consider the mechanical properties of Bucky papers, they're quite weak and brittle and fracture at just 1,000 microstrains. And because of this lack of control, the material is also very inhomogeneous and non-isotropic. Now, if we look at some of the recent results looking at the mechanical performance of these thin film composites, we can see that although Bucky paper specimens exhibit linear stress strain behavior, the material itself is in fact quite brittle, fracturing at 600 to about 1,400 microstrains. But if we can put this material, this carbon nanotube material, in a more flexible matrix, like an epoxy, we certainly get a very flexible material. But the problem is that the material behavior is highly nonlinear.
So your scale is what scale do you have to discuss? Megapascal, as you said?
Yeah, so this is the error in their publication, actually. So yeah, 2.5 megapascals is, I think, or 25 megapascals is what they're trying to say.
And the horizontal axis is assumably millistrain, not
Right.
actual
Right.
or something.
Yeah, so, yep, thank you for clarifying that. So as we continue our presentation, so the reason that we're getting this diminished performance is simply that, this lack of control, but it's also because that carbon nanotubes are inherently very challenging to use and to manipulate. It's because of their small size that they have an incredibly high tendency to agglomerate and to form large clumps. And if we can't engage individual particles or individual nanotubes, we can't take advantage of their impressive material properties. So if you consider the case when you mix carbon nanotubes into another liquid, what we obtain is a two-phase system as shown. Obviously, the carbon nanotubes are clumped together and precipitated to the bottom. And if we directly use that two-phase solution and try to create a thin film material, what we end up getting is a highly inhomogeneous thin film due to this lack of control. Now, on the other hand, if we're able to disperse or separate individual carbon nanotubes in some solution form, we can then better take advantage of this material to create a more homogeneous film characterized by a dense percolated structure of individual or small bundles of carbon nanotubes. And this percolated structure will become important later on in my discussion, and I'll explain a little more later on. So for our study, in order to enhance our control to manipulate these materials, we've actually taken advantage of a thin film fabrication technique known as the layer-by-layer self-assembly or template-assisted method. Essentially, the layer-by-layer method entails the sequential deposition of oppositely charged nanomaterials onto a charged substrate. So to better visualize this process, we can come with a charged substrate, such as glass or silicon or different types of polymers, and immerse them into a positively charged polyelectrolyte solution, such as polyvinyl alcohol, PVA, or polyaniline, PANI. But regardless, over time, the positively charged molecules will adsorb onto your charged substrate. Now, upon removal of your charged substrate and the adsorbed monolayer, we can then dip that substrate into a negatively charged solution, which in this case will be a single-wall carbon nanotube dispersed in a PSS, or polysodium styrene sulfonate solution. Now, by repeating this process over and over again for 50 or 100 times, we can then deposit a very uniform film onto a glass substrate, for example. Now, if we utilize scanning electron microscopy to explore what the micro and nano morphology of this material is, indeed, we do see a highly dense and percolated deposition of only individual and small bundles of nanotubes, as shown by these white lines, or in this zoomed-in picture. Now, this percolated structure is extremely important to us because carbon nanotubes behave as essentially highly conductive materials. So with a percolated structure, we can now conduct current from one end of the material to the other end. And in addition, by having a percolated structure, our material or composite systems will exhibit better mechanical performance. But in addition to being able to control the material at smaller length scales, the layer-by-layer technique is actually an inherently very versatile thin film fabrication technique. As you can imagine, we can easily control different carbon nanotube constituents by varying the type of solutions that we use. We can control the number of layers to vary thin film thickness for different applications. And we can even vary the solution concentrations to control how much of the material is deposited. So in more detail, we could vary the type of nanotubes used or other different types of nanomaterials or polymers. And we could look at the weight concentration or weight percentage between carbon nanotubes versus some other polyelectrolyte species, so as to tailor its electrical and mechanical properties. But all in all, these tuning knobs associated with layer by layer allows us to create a multifunctional nanocomposite that's encoded with specific material properties. So upon running the layer by layer technique, one of the first studies that we want to investigate is the inherent piezoresistive performance or strain sensing performance of this material. So upon thin film fabrication, we then cut a small rectangular piece of this specimen and mounted it on a tensile testing coupon. This specimen is then put in an MTS 810 load frame where we can then apply a tensile compressive cyclic load pattern to it. Now in order to sample or determine the strain sensing performance of this material, we can sample its resistance in real time using an Agilent digital multimeter. And from the results shown here, where we plot the overlay of the resistance of the material versus the applied strain, we see that this material behaves as an inherently good strain sensor. That is, the resistivity of the material increases in tandem with increasing strain. And furthermore, it's also repetitive. Now, as I mentioned before, with this type of layer-by-layer thin film fabrication system, we have the ability to encode different sensing mechanisms within the material itself. So instead of using polyvinyl alcohol, we can replace that with a pH-sensitive polyelectrolyte known as polyaniline and basically create our thin film nanocomposite again. So here, the objective is to develop a pH sensor that we can use for biosensing applications or even to detect the onset of corrosion. So to validate the performance of this material, again, we can cut up a small specimen of this thin film. We then mounted a plastic well onto the surface of the thin film, which will allow us to pipette in different pH buffer solutions to expose these buffer solutions to the surface of the film. And then again, we'll measure the resistance as a function of time using our Agilent multimeter. Shown here is the time history record that we obtained for the thin film as we pipetted in pH buffer solutions from pH 1 to pH 11. And what you can observe is that the resistance of the material actually increases in tandem with increasingly applied pH solutions. And furthermore, upon the addition of a pH 1 solution, the resistance drops back to its original nominal resistance. And we can see that the material behaves sort of bilinearly in the acidic as well as the alkaline domain.
Excuse me, I don't understand how you measure corrosion here.
Yes, so our objective is to basically encode or embed this material inside reinforced concrete. So we're interested in monitoring the breakdown of the passivation layer on the surface of the rebars.
Okay, the interface concrete and so on.
Right, right. So our objective is first to characterize the performance of this material, how it measures pH. So it's not a direct corrosion measurement, but an indirect way. Right. Now, in order to create a true multifunctional material where we can combine sensing, the material should also possess impressive mechanical properties. So upon thin film fabrication, we wanted to explore how these materials perform mechanically, basically. So again, upon etching the film to create a freestanding thin film, we can then mount it in a Test Resources 150R electromechanical load frame to investigate basically its stress strain performance. Now, before I talk about the carbon nanotube thin film behavior, we can first take a look at just a pristine PSS-PVA polymeric thin film stress strain response. Here you'll see that the polymeric material exhibits same behavior as a typical polymer, where you have an initial linear region, followed by some yielding and some strain hardening due to crazing of the material, and ultimate failure at very high strains, in this case 250%. Now, upon addition of carbon nanotubes using the layer-by-layer thin film fabrication technique, we see a dramatic change in the stress strain response. First, we see that we can dramatically enhance the stiffness of this polymer nanocomposite, to approximately 11.1 gigapascals, as well as to achieve high strength, approximately 250 megapascals. But instead of having a very brittle material, we see that the material is still pretty flexible, failing at about 7.4% applied strain. Yes?
What is the principle to make this material more ductile? Why? Why you go from a brittle to a ductile? What is the reason?
What, you mean compared this one to other films?
So what is the active ingredient which make it more ductile?
Are you referring to these two?
Yes.
So we actually don't get more ductile. The material becomes more brittle with the addition of nanotubes.
Yeah.
But we're exploring the trade-off between how we can improve mechanical performance, but we're just sacrificing for its ductility or flexibility, right? I hope that answers your question.
Well, this seems to be stiffer, but yet more ductile than this one. You are strain softening here.
Right. So this is failure at 250%.
Okay.
But this is in strains. This is microstrain.
250%?
Right. This is 2.5 million microstrains. Right.
250, okay.
That one is only 50.
Okay. Yeah.
Right. Right.
Yeah.
Okay. Now, if we compare the performance of this layer-by-layer nanocomposite with some of the other recent results, we see that we can improve the Young's modulus, tensile strain, as well as failure strain, or the ductility of the material, compared to bucky paper as well as epoxy resin composites. But what's more important to note is that this is really just a preliminary study conducted to explore as fabricated nanocomposite properties. And we can further optimize its performance by varying carbon nanotube versus polyelectrolyte weight concentrations, or even fine-tuning the chemical interface between carbon nanotubes and its bulk matrix. So a lot more work can be done to improve the material properties. Now that you have a general overview of what this nanocomposite material can do, I'd like to spend a little bit more time going into how we can combine this nanocomposite with a RFID or passive wireless sensing technology such that we can begin to use this material as an actual sensor for structural health monitoring applications. So as many of you already know, RFID is a common wireless sensing technology used in Target or Walmart, primarily for package tracking or security systems, such that if you walk out with an unpaid item, the alarm will go off. So this is primarily based on RFID. Now, just to give you a brief overview of RFID, the simplest system is comprised of two primary components. The first is a RFID reader, which is simply a coil antenna connected to some AC power source, like an impedance analyzer. And the second component of RFID is its sensor tags, such that the sensor is typically, when we talk about a passive system, the sensor does not require any batteries, and all the wireless communication as well as power transmission comes from the reader itself. So as you can imagine, the advantages offered by an RFID system is that it doesn't require any power. And because of the fact that it doesn't require any batteries, it can be fabricated of a small form factor, generally using thin film technology, as shown by these Texas Instrument antennas. And because of their small form factor, they become ideally suited for embedment within structural materials like concrete or composites. And you can control their material properties so that they're essentially durable as well as low cost. But something important to keep in mind is that the main disadvantage for RFID is its short communication distance. And that's primarily because it doesn't have an active power source in order to broadcast the data that it collects. So just to go into a little bit more detail of how an RFID system works, here we have an RFID reader antenna that's connected to our AC power source, in this case an impedance gain phase analyzer. Now when we pass an alternating current through this coil antenna, we know that physics will tell us that we can generate a magnetic field through the coil of this antenna. Now if we come with a sensor tag with a corresponding coil antenna within the vicinity of this generated magnetic field, we know that inductive coupling will guarantee that we generate a secondary potential drop and current flow in this sensor tag. And this potential drop can be used to power our passive wireless sensor, which could allow you to collect data, to measure whatever you're interested in. So in order to get the response from your sensor tag, all you have to do is just measure the change in impedance of your reader antenna to see how the impedance changes as a function of some of the external parameters that you're interested in. Now, first, if we consider just the reader itself where there's no sensor tag, and we measure the impedance of the reader antenna, we see that the impedance as a function of frequency, or the impedance magnitude to be exact, looks almost like a straight line. Now, when a sensor tag, whether it being a parallel resonant circuit or a series resonant circuit, when it comes within the vicinity of this reader antenna, we immediately see that we can observe resonance as governed by the resonant frequency of your passive sensor tag. Now, if your sensor is designed so that its resistive component changes as a function of this external applied stimuli, we know that the bandwidth of the system will change, which is schematically shown as what you'll see when you look at the impedance of the RFID reader. Now, on the other hand, if you can design a capacitive sensor, we know that the resonant frequency will govern a shift in the resonant frequency response, which can also be detected wirelessly using your RFID reader antenna. Now, the objective that we want to achieve here, like I mentioned before, is to design a corrosion sensor that we can embed in reinforced concrete environments to detect the onset of corrosion by measuring changes in pH. Now, in previous studies where we characterized our Pani pH thin film, we've only been applying direct current and measuring its resistance. But we really need to take advantage of electrical impedance spectroscopy to look at whether the material behaves as a pure resistor or does it have some capacitive element or even sensitivity to pH to it. Now, just to, without going into too much detail, electrical impedance spectroscopy, or EIS, is simply very similar to a 4-point resistance probe measurement. But instead of applying a DC current to the material, in this case, we can apply a range of alternating current to the material. And instead of just measuring the resistance, we can measure impedance, which is inherently a complex quantity. And this impedance information that you get will be encoded with some resistive, capacitive, and inductive behavior of the material. So upon taking our pH-sensitive thin film, we then performed impedance spectroscopy on a number of these thin films subjected to different pH buffer solutions. Now, if we look more closely at the data, one of the first observations that we can make is that we can observe a semicircular response in the complex impedance domain. And this semicircular response suggests that this thin film behaves as a resistor, capacitor, parallel circuit, which allows us to model the behavior of this material. Now, what's more importantly is as we increase pH from pH 1 to pH 13, we see an increase in the radius of this circle, as well as a movement of the hypothetical center of the circle. So to investigate what this material behaves like, we then fitted the experimental data to a simple RC parallel circuit, where we can then back out the calculations and look at how the resistance and capacitance changes as a function of applied pH. So upon model fitting, using a simulated annealing algorithm, we see that the pH thin film does in fact behave bilinearly, where in the acidic region, the material has a pH sensitivity of approximately 1 kiloohm per pH. But in the alkaline domain, where it's important for reinforced concrete corrosion studies, the sensitivity is much higher, approximately 15 kiloohms per pH, which suggests that there is some promise for using this type of material for detecting pH changes. Now, to combine our nanocomposite with an RFID technology, we first utilized printed circuit board technology, where we can then design and pattern our reader antenna printed on an FR4 laminate substrate, as well as a corresponding sensor tag antenna with some inherent electrical contacts for surface mounting different discrete elements, circuit elements, such as capacitors or resistors, as well as a region where we could use this material as a substrate in order to deposit our carbon nanotube pH-sensitive thin film. So schematically shown here is how we can fabricate our thin film, where we can take our material, your printed circuit board material, epoxy coat it for electrical insulation, and then dip it into your various solutions to deposit your nanocomposite sensor. Now, upon sensor fabrication, this is one of the prototypes that we have, and the sensor is about an inch by an inch, or 2.5 centimeters by 2.5 centimeters. Now, one of the first studies that we've conducted with this passive wireless sensors is to validate its wireless as well as pH sensing capabilities. So first, we then utilized that corresponding reader antenna, coupled it with an impedance analyzer to try to wirelessly interrogate these passive wireless sensors. And as you can see from the impedance magnitude response, we do observe this resonance behavior at a resonant frequency of 3 megahertz, which is characteristic for the sensor that we designed. But more importantly, we also see a change in the reader impedance response, suggesting bandwidth changes. So if we back out the bandwidth of the system, we could see that indeed the bandwidth does decrease as a function of increasing pH. Now, this is one of the preliminary studies that we've gotten, and now we're looking at how we can improve the sensitivity of this material, as well as how we can embed these materials in actual reinforced concrete specimens. But from that previous example, you probably saw that, in fact, we can design a wireless sensor using this type of nanocomposite system. But up till now, for today's presentation, I haven't presented anything new to you, right? In the sense that we have our thin film, we can use it as a discrete sensor. We can combine that with a passive wireless sensing technology and use it as an embedded sensor, but it's still a discrete sensor. So we haven't been able to achieve our goal of 2- or 3-dimensional spatial sensing, and not even direct damage detection. So in order to overcome this limitation of indirect sensing and discrete sensing, we're actually going to take a different turn and basically look at some of the examples that we see in nature. Now, for example, if we consider the human dermatological system, you can easily tell that our skin is, in fact, an inherently multifunctional material. We know that our skin is incredibly strong, and it can keep bacteria or different germs out from our bodies. Our skin can also regulate our temperature so that everything is functioning properly. And our skin can also absorb nutrients, such as vitamin D from sunlight. But more importantly, our skin is actually a very good sensor. And as you can imagine, your skin can detect the occurrence of a crack, or in this case, a scrape, or some type of damage that has occurred on the surface of the skin. But more importantly, our skin is also an inherently very good multimodal sensor. That is, in addition to being able to detect a scrape, for example, or a bruise, your skin sensor can actually detect flow of air along the surface of the skin or variations in temperature. And this is the model that we want to achieve in order to develop some type of artificial skin that is not only capable of identifying what damage has occurred, but also the precise magnitude and location where the damage has occurred. So if we consider this idea from a structural health monitoring aspect, if, for example, we have a welded moment connection, and in this problem, we're interested in identifying or determining the spatial strain distribution at this welded moment connection, the current generation structural health monitoring paradigm will force you to instrument a set of strain sensors or strain gauges, where you can directly measure the strain at these instrumented locations. But in order to estimate the 2-dimensional spatial strain distribution, you would have to take advantage of interpolation between your sensor nodes in order to get some corresponding strain distribution map. Now, the objective of this part of the study is, instead of relying on distributed sensors, we want to come up with a material that is sensitive to damage at every location. That is, we want to deposit what's known as our carbon nanotube-based sensing skin onto the entire welded moment connection, so that we can directly measure strain or other damaged features directly, but also to identify damage location precisely. Now, in order to achieve this goal of spatial damage detection, we've coupled our thin films with a technique known as electrical impedance tomography spatial conductivity mapping reconstruction. So if we consider, just to give you an overview of how EIT, this electrical impedance tomography, works, we can first look at just any conductive material instrumented with a set of boundary electrodes. Now, if we inject direct current or alternating current at a set of boundary electrodes, and we know the conductivity distribution of the material, we can utilize the Laplace equation to determine and predict what the boundary voltage measurements will be, or what the boundary potential drop will be, assuming that we know the conductivity distribution of the material. But the problem that we're trying to solve in this case is actually quite different. You can imagine that if I had a material, I can easily instrument my boundary electrodes. I can easily take a current generator and apply current to the material, and I could then also grab a voltage generator to measure the potential drop of the material. But what we're interested in is actually to determine the two-dimensional spatial conductivity of the material, since we know that conductivity of the material is directly related to some damage feature that we're trying to measure. So in order to achieve this goal, we can begin by relying on finite element formulation to mesh our material into individual triangular elements. We can then assume a conductivity distribution for this numerical model, apply our fictitious current to it, and predict what the boundary voltage output will be using the Laplace equation. We can then compare the predicted boundary voltage output with our actual experimental measurements, and basically iterate this process by minimizing this cost function to minimize the error between your predicted as well as experimental measurements until the error between the two is less than 0.05%. Now, upon solving this inverse problem, we can then go back and output what the conductivity distribution of our material is. Now, to validate this, so you can see that if we had a thin film structure, we can then easily experimentally instrument this material with a set of boundary electrodes and basically perform this experiment in the lab or in field conditions. But before we move out into field environments, we have to begin by validating this EIT technique combined with this nanocomposite system. So to validate this technique, we fabricated a plethora of different types of films. We can run the EIT algorithm to obtain some initial conductivity distribution. But what's more interesting is we can actually mechanically etch out different patterns on the surface of this thin film to create regions of zero conductivity, where we can then run the EIT algorithm again to determine and estimate its spatial conductivity and compare that to its original baseline conductivity map. And what you can see is that the conductivity difference for these different thin films correspond to the experimental pictures that we've taken, thereby validating that this technique has some promise to detect changes in conductivity. Yes?
You went from conductive material to zero conductivity. What happens if you have grayscales, like a reduction in conductivity, for example?
Yes, that's a very good question, actually. I'm going to jump out to a different slide. It's not actually, well, I'll answer your question first, and I'll go to a different slide to show you. Okay. But basically, to answer your question, yes, we've also created gradients of different conductivity by varying the thickness, and it can also detect the corresponding changes. Yep. So upon validating this technique for measuring changes in conductivity, our initial interest is to utilize this sensing skin approach to detect impact damage for aerospace or naval applications. Now, in order to basically perform an experimental study to see if our sensing skin can detect impact damage, we've deposited our thin film onto a 110 by 110 millimeter squared aluminum plate. We can then create this impact testing apparatus based on this pendulum structure, where we can vary the mass of the pendulum as well as the length of the pendulum in order to precisely impact our plate at different locations, as well as with different impact damage magnitudes. Now, upon impacting our plate at 4 different locations with 4 different impact energies, where 1 corresponds to the lowest energy and 4 corresponds to the highest impact energy, and here we're looking at the same piece of material, but one from the front view and one from the back view, where the back view is where the impact hammer directly strikes your plate. We can then run this EIT algorithm on our sensing skin and basically map out the 2-dimensional conductivity of our material, where you see that regions where you have impact damage light up on this conductivity map. And the change in color corresponds to the change in conductivity, which also correlates to the magnitude of damage. So now with this technique, not only are we able to identify the magnitude of damage based on change in conductivity, we're also able to isolate where the location of damage has occurred And you can see that we could plot it in 3D for easy visualization of damage. And we can do some data analysis to look at how impact damage, how the percent change in conductivity varies with impact energy. And we see that we do see some linear behavior.
This is damage in the film itself, right? Or in the,
This is damage in the plate itself.
in the plate?
So there, we purposely try to inflict some permanent deformation on the plate. There is a film. Yes, there is. So the plate itself is silver, but after we dip the nanocomposite onto it, it's a black thin film.
Can you explain why the front and the back is different?
The-
How are they different?
So this is one plate coated with two films on two sides.
Yeah.
So the back of the plate is where the impact hammer strikes, and the front of the plate is the other side. And your question is,
How come I only see two obvious feet versus the other one has 3 feet?
right, that's a good question actually. So for some of these cases where we have high impact energies, the impact hammer actually etches off a little bit of the film, thereby imparting greater conductivity change. So some of these peaks correspond to the film being damaged in addition to the structure being damaged. But yes, you're right.
So are these location of the impact or the damage?
These are locations of the impact.
Both front and back? Or?
Right, both front and back. Right. So I think his point was, why is this peak, I guess why is this additional peak showing up versus the bottom peak? Yeah, I think that's a very good point that we are looking into, why we do see that conductivity change. I mean, if anything, I think it would make sense to have 3 peaks on the impact surface and 2 peaks on the front. But yeah, but but one of the things that we did notice from our study is that when we impact the plate, even though we are physically etching some of the material off, we are imparting so much deformation that we do see some film peeling off of the surface, as shown by the cracking. So this might result in a greater conductivity change in the material at that location.
So I'm sorry, the change in conductivity is due to a pre-existing condition in the plate or to damage induced by the hammer?
The change in conductivity is due to the thin film that we deposit onto it, but the change in conductivity of the material is caused by permanent deformation of the plate.
Pre-existing
Due to impact.
Due to impact.
Right, right. So initially, if we look at just the conductivity map, it's just uniform. Right. Okay, so previously I also mentioned to you that we're interested in developing a corrosion sensor based on this polyaniline type of thin film. Now, in order to validate or demonstrate that we can detect corrosion, we've basically deposited this thin film onto a steel substrate. We then etched out 2 regions on the steel substrate and then mounted on 2 plastic walls on the surface. Now, the point of etching out the steel and exposing the bare steel substrate is so that we can pipette in different salt solutions to accelerate corrosion while simultaneously measuring the 2-dimensional spatial conductivity just to see if we can detect the growth of corrosion as well as where corrosion is occurring. So what I'm going to show you next is just a brief video of overlays of EIT images. So initially, we don't see too much happening, but over time, as salt attacks the bare steel substrate, we see corrosion developing and a corresponding change in conductivity of the material at these locations. Whoops. So yes, I'm sorry. Oh, okay. Too sensitive. So just to summarize my results, first, today I've presented to you the development of our carbon nanotube composite using the layer-by-layer approach, where we could look at multimodal sensing as well as its mechanical performance. Then we've combined our nanocomposites with an RFID technology to try to see if we could utilize this device as a passive wireless sensor. Today I've showed you how we could use it for pH sensing, but we've also have corresponding studies for strain sensing and so on. But more importantly, to address the current limitations of structural health monitoring, we want to be able to achieve 2-dimensional and direct damage detection. And that's how we arrived at the development of our bio-inspired sensing skin, where we could directly detect impact damage, location, as well as severity. And we've also begun looking at corrosion and how that affects thin film properties. So with that, I'd like to thank you very much for your attention, and I'd be happy to answer any questions.
Do we have questions? Yes?
You talked about two different detection mechanisms in the second and third parts of your talk. You have changes in capacitance and changes in conductance.
Yes.
I would imagine that both pH and stress would change both of those quantities.
Mm-hmm.
Do you have a way of separating them out?
Yes,
They're
that's
based on magnitude or time scale?
That's a very good question, actually. So upon looking at our electrical impedance spectroscopy studies, it turns out that even though the material behaves as a parallel RC resistor capacitor type of circuit behavior, only the resistive component is responsible for whatever stimuli that you're measuring. So in this case, if you want to combine your strain sensing film with your P sensing film directly onto one material, it would be almost impossible to separate the two responses out. But what's advantageous about EIS in spectroscopy is that we not only have just direct current applied to the material, but we could look at a range of frequencies. So right now we're interested to see if the strain sensing component is only limited to, say, low frequency, whereas phase sensing is limited to high frequency. Yeah.
My question is, what if your something like graphite is thick and the damage does not occur on the surface? Does it make sense that?
That's a great question, actually. So our current technique is only limited to surface damage. So the thin film is coated on the surface. So to answer your question, if it's too deep in there, no, we can't detect it if we can't observe any surface response. But what's interesting to note is that this EIT algorithm is currently being adopted as a 2D methodology, but it can be easily separated or to basically apply to three-dimensional problems. So if you had a material, a thick material that's sensitive to damage or changes in, due to cracks, things like that, you can directly use EIT to figure out the location of damage. But that's a different study, I guess. Yeah. Thank you. Yes?
I guess you could, irrespective of trying to measure damage,
Mm-hmm.
you could use this thin film to image the response on the surface
Yes.
for all sorts of other applications.
Yes, yes. So in fact, one of the issues with nanocomposite fabrication is how good is your nanocomposite, how homogeneous it is. And one of the ways of characterizing it that we see is we could directly use this technique to look at how the conductivity is distributed.
So what is it, if you wanted to image the formation of the surface, what's the resolution that you have in this case?
Oh, that's a great question. So the resolution, so let's just use this for example, is directly related to the distance between your boundary electrodes.
Nothing to do with the size of the
material?
Yes.
There is some limit to it, but right now the resolution is governed by right. So, but if you look at the material itself, if you go down to the micro scale, where you only have a few carbon nanotubes spanning maybe 1 micron by 1 micron, then obviously this region compared to the region next to it might be very different. So the material is very inhomogeneous in that way, and the response can be very different. So I would say there is some limit to how fine that we can get, maybe tens of microns where we go past at least 1 or 2 lengths of nanotubes.
How are these bonded to the surface?
These are directly deposited onto surfaces. So the bond is actually quite strong using electrostatic.
If you do deposit on a grate, would you spray it, or how would you?
Yeah, that's a great question, actually. So there are many techniques that we can do. For example, if we wanted to create a freestanding thin film, we can etch the substrate to release the material. And this technique can be scaled up to poster sized. You can embed this material in spray paint cans so that you're doing layer by layer on the bridge surface. So there's a variety of techniques that, that's out there that's available to us. Great, thank you.
Okay, I think we have no more questions. Well, let us thank our speaker again. Thank you.
Thank you.